I am pleased to introduce Professor Robert Fuller, my thesis advisor in Northwestern, and currently he is the president of Ample Incorporated, and he did his bachelor's from MIT in mathematics and master's in statistics and OR from Stanford University, and his PhD was done under the supervision of George Danzig, who actually invented linear programming. So after that he joined Northwestern University in 1979, and from 79 he was a faculty in Northwestern University. Recently he has become an adjunct, and during this time he has actually published in several international leading journals like Management Science, Operation Research, MSOM, and other journals like Decision Support System, ACM Transactions, Math Programming, Science Journal of Computations, and several leading journals. And I have been fortunate to work with him, where I could figure it out that how actually good programming could be done, because I was never a good programmer, but little bit I could learn from him. He is now full-time the president of Ample Optimization, and Ample, as you know, is a modeling language which is considered to be the most probably or one of the most important modeling languages, and which is, I think, Optimization has done differently today. Because of his seminal paper he came out with in 1983 in the ACM Transactions, how modeling language should be there in the future, and he came out and demonstrated with an Ample that this is the way modeling languages should be there. So with that I will hand over to Bob Fuller, and he is going to discuss, he is going to talk about his optimization software systems and operation research, best practices and current trends.
Okay, you can hear me. Well, yes, I have. I think it's all right. And so thank you very much, and I really appreciate it that you invited me here. I'm happy to be here and to give you this talk. And this talk is an attempt to look a bit more systematically at how modeling is done with optimization, and the approaches that people use, and why certain approaches have become popular. And so this is from the upcoming ORSI meeting. I took all of the titles and put them into a word cloud, and you can see that model is going to be a big a lot of this talk is going to be about model-based optimization, and there's a lot of optimization here as well. And I think you do this with any operations research conference, and these words pop up very frequently. And so I really don't need to define this here, but I just thought I'd put in an introductory slide saying that by optimization, I mean you're given some objective function, and you want to choose the values of the variables to optimize that, subject possibly to all sorts of restrictions. And so that's the kind of optimization that I'm concerned with, is one that you can write somewhat in this way, in terms of decision variables and objectives and constraints. And I'll distinguish two approaches to optimization that have been seen ever since people started doing this sort of thing. And I give an example of this. I'll just take a calculus example. Suppose you want to find a local extreme, a minimum or maximum of just some function where it's a differentiable function. And there are two approaches you could use to solving this very simple optimization problem with no constraints. And the first approach, you form the derivatives of this function, and then you find some expression for the solution. So you form the derivatives, you set them to 0, and where the derivatives are 0, the gradient of this function, that's really a vector of partial derivatives, then where that's 0, you know you have a locally optimal point, or at least a candidate for one, and so you just find an expression. You have to actually solve this. You sit down and you say, well, I can substitute this for this and divide through by this and so forth. And so that's one approach to doing it. And another approach is choose a starting point and then do some iterations. So start with x0 and get each iterate xk plus 1 from xk by adding on some step direction, where the direction is the solution of these equations that involve the first and second derivatives. This is called Newton's method. It's been around for hundreds of years, and you keep doing this till the iterations converge. And the question is, what's different about these? And the first thing that would occur to you is, boy, this has an algorithm and this doesn't have an algorithm. Okay? But I would argue that there's a deeper difference between taking this approach and taking this approach to solving a problem like this. And that is that they differ in where you put your effort. Okay? So when you take number one, I call this method-oriented because really all your effort goes into finding a method for solving this. For each new F that comes along, you have a new challenge. What method can I use to derive a solution to that? And so you need a mathematician to study that and come up with some clever way of characterizing the solutions. Okay? And that's really where the effort goes there. In two, which I call model-oriented, really all the effort goes into choosing the F. Once you have F, you can apply this same Newton's method to any F. So really, then there's no more thought on your part. You don't have to figure out how to apply Newton's method. You just have to decide what the right function is to model your problem. And in fact, we'll see, you can implement that by general off-the-shelf software. So the idea is you don't even worry about any sort of method. The method's already been implemented by somebody who sat down and wrote a package for running Newton's method. And all you have to do is tell it what F you have. Okay? And you might ask here, well, didn't I leave something out? Don't I need to compute the gradient and the Hessian here? Remember, Newton's method, the step depends on solving some equations, some linear equations involving these, right? And my software solves the linear equations, but where does it get these derivatives from? And the answer is yes, the software does everything. So software handles everything. I have not left anything out. The software, I give it a description of the function f, and it computes all the function values that might be needed, and more importantly, it computes all the derivatives as well. So all you need to do is write an expression for what you want to be optimized. And so you concentrate on that. That's our model-based optimization. It's your model of the real world, your function that's important that you spend your time on. And then to solve it, you just apply this algorithm, and it does all the computing and so forth. And that's an off-the-shelf piece of work. And here's a small test case. This function has a number of locally optimal points. And here's what it looks like mathematically. You're given 2 parameters and all this data here. And you need to determine some variables and to maximize this. So it's a well-known test problem. It generates a number of locally optimal points, and Newton's method will find you one of them, depending where you start. And you see that this is highly nonlinear. There's a squared, and this is all we take the inverse of this. And so how do we do that? And so if you've seen the ample system, you've seen one way of doing this, but let me just show it. I can go here, and that's what's called the Shekel problem. So there's the model. Okay? And I can write the same thing to a computer. Let's see, there it is. I can say the same thing to a computer that I wrote down. So this is exactly my same problem that I had on the other slide. Okay? But I've written it in a way that the computer can read. So here's the sum 1 to m, 1 over ci plus the sum j equals 1 to n, this squared, so forth. So I can actually put all that into the computer, and then I can get the data. There's the data. Okay? So separately, I can say what all those parameters were. If you looked in here, you saw that there were some parameters m, n, a, c, and in my data I say what they are, but if I change them, I get a different problem. Okay? And then I can go here, and I can go to this thing here. Let me just do it this way. And I can go model shekel.mod, and I can go data, that, and then I need to set some initial points, right? So our initial points were, I need to set the values for these x's from 1 to n. So in this case, just to do that quickly, I'm going to say let J in 1 to n x j, I'm just going to say, let's just randomly pick it. Random starting point, uniform 0 to 10 or something like that. Okay. And then I pick a solver. So option solver, nitro, say. So I pick nitro. There are all these off-the-shelf nonlinear solvers. Okay. They can all solve unconstrained problems. So I just pick that, and I can solve it. And it gives me an answer, and I can display X. So that's sort of what I mean by model-based optimization. All I'm doing is specifying the model, and notice that I might have spent a lot of work getting that model file the way I wanted it, picking just the right test problem, but once I did it, okay, all the work of computing all those derivatives and everything else that went into solving this happened separately. And then if I want to check it, I can pick a different solver and, gets this. I sent the first solution in, and it confirmed, yes, it thought that was an optimum. And so you can switch between them very easily. And so that's a simple model-based approach. And you can see the same thing here. Here's my math, and here's that description that I had. Here's the data. Here I run it with Nitro. Here I run it with Loco. Okay. And so that shows sort of the feel for that kind of thing. But that's very simple. If this is really going to work, it has to work with all more complicated things. So here's a complicated example. It's unconstrained optimization. There are 8 index sets and 30 different parameters indexed by them. There's one variable, one collection of variables that's really the variables. The idea here is to minimize the energy of a protein molecule, to find a configuration that minimizes the energy. Okay? It's believed that that's the configuration that the protein will actually have in nature. So there's been a lot of interest in actually trying to optimize or model what's going on there to try to figure out what configuration a protein will have that you might synthesize. The problem is there are many locally optimal solutions, so you have to actually solve it from many starts. And there are 28 variables that are defined in terms of the problem variables. So the problem variables are where the molecules are, and the other variables are various functions of that. And eventually you get an objective that's the sum of 6 variables that represent different kinds of energy. So this looks much more complicated. Here's the variables, the positions of the variables, okay, and set to some initial value. And then in red, I've just shown some of the nonlinearities, okay, cubes and squares and 6th powers and so forth. And then there are 6 components. Here's an arctangent. There's 6 components of energy, 1, 2, 3, 4, 5, and 6, and then minimize the sum of those 6. Okay? Now, in this case, you can't even think about computing a formula for the derivatives yourself. I mean, each of these is a function of other variables, which are functions of other variables, which are functions of other variables, which are eventually functions of the x variables, which are the real optimization variables. And all that needs to be substituted out so that you eventually, this gets reduced to a function of just the x's. And then you need to solve the problem. And at each step, you need to compute the first and second derivatives of this huge function, which I mean, you would have trouble even writing it down without making a lot of errors, let alone trying to write a formula for its derivatives or program it or anything. And so this is a much stronger case for where you need model-based optimization. Someone spent a lot of time thinking about this model, okay, and there are a number of variations of it. But when they come to solve it, okay, you don't think about what's the method you're going to use. Okay? The method you're going to use is just Nitro or something. It's going to come there and solve it because it's a differentiable set of differentiable functions. Okay? One big function. So there's quite a bit more work that goes on there. But it turns out it's not a whole lot harder. to solve. So if I go back here, I can get rid of this example. I actually want to show that it's fast, right? So this is called p-fold. There's the protein folding model. And here's all the data for it. It's a long data set. Okay? This is all the data that goes for this particular protein. Okay? And then I go here, and I reset, and then I can get rid of all this, start over, and say model p-fold, was it p-fold 3.mod, I think? Oh, p-fold, I know. Model, let's take a look at that again here. They're called p-fold mod and p-fold 3.dat. Okay. So let's get rid of this and clear it out. Model p-fold.mod, data p-fold 3.dat, and option solver nitro, say, and solve. That's all it takes. If you want to see X, there it is. That's the positions of the thing. Essentially, it's there are 22 different atoms in there, and these are the coordinates in 3 dimensions. So that tells you where it came. And so you see that you can quickly get to a point where the model is understandable, but the work to actually implement the method is impossibly complicated. And this is still a small problem, and yet actually the derivatives can be computed automatically very quickly. Okay. So go back here, and this is just the same thing. And here I actually ran it again, and I asked it to show some details of the algorithm. And you can see it took 13 iterations, and it shows what it did at each step and so forth. And it had a number of function and gradient and Hessian matrix evaluations and so forth. So it's actually, doing the work you expect it to do. Okay? But it figured out what the function was. Okay? And so, yes?
Can we also visualize the solution somehow?
So,
In a 3D way?
yes.
Or where the protein is folded?
Yeah.
So can we visualize exactly what is the minimum energy configuration?
Yeah, so you could, so the visualization tends to be very problem specific. So rather than trying to build a visualization into this system that I've shown, what we've done is provide hooks to other systems. And in particular, once you get the model running, it has programming interfaces or APIs that you can use to build this whole thing into a bigger system. And your bigger system might have all sorts of things for generating data, keeping track of cases, and also for visualizing the results. Okay? And it's certainly important. So the origins of this model-based optimization, I deliberately used something very simple here, but it did not have its origins with unconstrained nonlinear programming. And of course, unconstrained problems went all the way back to Newton, and people really did do them method-based by solving the equations. But what really forced people to look at this was linear programming. Okay? And linear programming on computers, which started in the early 1950s, which is already quite a while ago. And so this is where we have linear expressions, so various things that are proportional to the amount of activity. And we have inequalities. The important thing about linear programming is that you have linear expressions for objective and constraints, and you have some constraints which are not just equations. Okay? And if they were all equations, it would be trivial, but like some of the variables have to be non-negative, and there are various constraints like these shown here, okay, which are not quite equal. Okay? It's not required that you ship exactly the amount available. It's just that you ship no more than the amount available. Okay? And it was these inequalities that made it hard to actually study these problems at all for a long time. People studied equations. And then there's an objective function that's usually some sort of minimization or maximization of familiar things like costs and distances and profits and flows. So when people started looking at these, they strongly forced them to think about model-based optimization for a couple of reasons. First of all, solving these things requires an iterative algorithm. There's no way that you can sit down with a pencil and paper and do any sort of reasonable solving of a problem with more than just a few variables. And so really, algorithms became essential to even consider this. In fact, nobody really paid much attention to linear programming until computers were about to come along, and they thought they had a possibility of getting a machine to do the computations. Otherwise, just the most trivial problems could be solved, and even then you needed a whole room full of people with calculators working for days. And the other thing, though, was that the algorithm here was not so easy to implement. You have to remember that computers back then were quite limited, okay? But it's true even today that to get these algorithms for these linear programs to run quickly requires quite sophisticated implementation. Okay? And you don't see this in a lot of textbooks which purport to tell you an algorithm for linear programming that's very simple and that you can almost do by hand. And maybe in the last section of the chapter they mention that this algorithm they're describing, well, you know, really doesn't work on computers and you have to do something else. Okay? But the real thing you need to do to be able to solve these is quite complicated. And for that reason, the idea that you would implement a special simplex method for every problem that you came across would not work. I mean, it's not the sort of thing where you can just sit down and write your own because you know exactly what your problem is. You really have to take a model-based approach where there's somebody writes a really fast implementation of a solver for linear programs, and then you just concentrate on coming up with linear programming models that are translated for that solver. Okay? And so this idea of using like off-the-shelf solving software and concentrating on the model was forced upon people by the difficulties of doing linear programming compared to the other problems that I showed. Okay? And here you can see the original paper that proposed all this by Danzig, which was, I think, actually published in 1948, or at least he gave the talk, the original talk in 48. And even then, at the end of this paper, he says, well, we think there's great potential for doing this kind of thing on computers, which are just now becoming available. And I think at that time, there were only like 2 or 3 computers in existence. And so here's an example of what kind of problem people really wanted to solve in linear programming, and they look quite different from my simple examples before. Maximize profits, which is revenue less production and inventory costs, subject to times available, and inventory is being carried from one week to the next. So it's a simple production inventory model, but in the mathematical formulation, we have 2 sets, products and periods, and we have all sorts of operational data. You see, now the data is getting quite complicated. There's amounts you can produce and initial inventories and hours available and demands. And then there's data relating to the objective function, production costs and inventory costs and revenues per unit. And so you have quite a bit of data for this problem. And now you have 3 sets of variables. Okay? How much to produce each period of each product, and how much to inventory, and how much to sell. Okay? How much you're going to sell. And so the constraints and the objective relate these 3. The objective is to take the revenue minus the costs. Okay? And the constraints are the amount of production time used must not exceed time available. First period inventory must be as given. And this relates inventories from one period to the next, okay? From period T minus 1 to period T. And sort of it's a material balance. It says that what you make and take out of inventory must equal what you sell and put into inventory. And then it says that sales are limited by the demand, so you can't plan to sell more than what you think you're going to be able to sell. Okay? So there's a whole complex thing of this, and this is typical of linear programming models. They're not just one variable and one simple constraint. They're all sorts of things. Okay? And so what happened when people tried to do this? Okay? So this is the next thing. People actually wanted to apply linear programming, and they had to apply it to these complicated things. And they found that they had this cycle they had to do, that they would get from the client some problem that they wanted to solve, and they would build a model like we've seen, like I just showed. They prepare some data. Notice the model didn't have any data in it, but they're going to have to get some case to run, some test case. Okay? And they generate an optimization problem, submit it to the solver, and they get some results, and then they send it back to the client, and the client would tell them that those results are not right, and that they never do this and that, and this is not physically feasible, and besides, we'd like to have this other cost taken into account and a bunch of other things. And so you end up going through this cycle over and over again to try to develop the model. Okay? So it's not true that you just sit there and you figure out a model. And now that you have one, okay, you can go get some data and solve it. You keep changing the model until you get it right. And maybe even after that, it changes over time. And so to manage this, the goals for optimization software were not just to be able to solve these linear programs, as people soon realized. They were to be able to repeat this quickly and reliably and get some results, and then finally have something you could deploy for the client. And this also sort of pushed people toward model-based optimization in a natural way, because what I described is the way that people think of problems. Okay? My description there was the way you might describe a problem to another person. But to actually solve these using the software that people developed, it needed this complex data structure, okay, which is just sort of it's a representation of a big matrix of coefficients, but only the non-zero coefficients. Because you see, only a few variables appear in each constraint, as you could see from my description, which meant that this matrix of coefficients, every constraint had only a few variables, and the rest had coefficients of 0. So you had to store only the non-zeros, and then you had to solve all the constants in the equations, and all the coefficients of the variables in the objective. And this information, with some refinements to make it easier for the solver, had to be produced there. And it looks nothing like the way you think of it. So there's this really disconnect between what the solver needs and what the modeler wants to provide. Okay? And the difficulty of going from one of these to the other was responsible for essentially linear programming being oversold in the early days. People were really enthusiastic about it when they first found that they could solve these problems, and then they found that the people who were supposed to be using it were not as enthusiastic, and found it took much longer to get any sort of project working than they had hoped. Okay? And so the challenge was to find some way of translating between these two forms that would be more reliable than just having somebody do this themselves. And so there are basically two approaches to this. One is what I call matrix generators, which are that you write a program to do this translation. Okay? Write a program that reads the data and for your problem translates it into that matrix, okay? Sends it to the solver. The solver sends you back a solution, and it translates it back into that. So the solver sends you a solution. It's a vector of length 375 of all the variable values, and then you figure out which are the production variables and which are the sales variables and the inventory variables, and you take it back and you prepare a nice report. So one thing people did was for each application you would write another program, okay, that would do this, and your program had the model built into it. And this could give you the power of a general language. I mean, you could do anything. You would write it in a language, and you could also do any sort of data handling and visualization and stuff you wanted. And or there are also some specialized matrix generation languages for this purpose that would help you out somewhat in doing this work. But the great disadvantages are that debugging these programs was extremely difficult. And you can see why. Imagine that you have this big production inventory problem in mind, and you have this in mind, and you decide to write a program to generate the whole matrix for the solver and to get the results back. So you write your program, and you get the data, and now you run your program, and the solution comes back, and all the production variables are 0. Or worse yet, it comes back and it says there's no feasible solution to the constraints. okay? Or, I mean, there are any number of things that could be wrong with the solution. And now you have to think, what is the cause of that problem? Well, maybe you left something out of the model. For example, you forgot the initial inventory constraints. And so it just set the initial inventories to some arbitrarily large amount and never produced anything, okay? That's one possibility. Maybe you made some mistake in the model or made a mistake in the data. The amount of time available is just too small to produce what you need. On the other hand, maybe in your program you got some loop index wrong, okay? Or you wrote some statement in the wrong way, okay? And you just made some programming error. Well, the problem is, how do you know what the problem was? You can't, all you know is that all the variables came out 0. And you have to, based on that, you have to go back to your program and try to figure out where the problem was and to figure out whether it was a model problem or a programming error. And this kind of debugging is very difficult, okay? And it's worse yet when you have to go through many iterations. I said there was a modeling life cycle where you had to keep updating the model until the client liked it. Well, every time you update the model, there's a chance that you'll introduce another programming error, and you'll have to go through all this again. And so this made it very difficult, especially then even if you got it working, somebody might need to come along and maintain it and make some changes. And the program that you write doesn't look like the model. And there's sort of the difference between the model part and the data part is hard to see. And because of all these things, it's the challenge to really maintain an application using this matrix generator approach. And this pushed people in favor of a model-based approach, okay? And which I'll describe here. And just to give you an idea of how frustrated people are, this is from 1980. So remember, the simplex method got started in the 1950s, okay? And there's a lot of enthusiasm about it for a couple of decades. By 1980, somebody was saying that the size of general LP problems being run has remained stable, okay? And up to 3,000 constraints. 3,000 is large, 6,000 is the largest people do, even though solutions have gotten much faster. And they say the cost of optimization is just not the dominant barrier to LP model implementation. Why aren't larger models being run? It's because they become unmanageable. So you see people actually writing this, saying that like they managed to get the computers faster and faster and to make the solvers go more and more efficient, but they had run up against this problem that the software for actually managing the models could not keep up with it. And it was this problem that around just this time, people began to look at these modeling languages. And the idea is that you would write your model in the same way that you think of it. And you've already seen a couple of examples of that. Okay? And in a way that the computer could read it. And then you would prepare data and let the computer translate all that. Okay? And this was really forced on people by the nature of linear programs and the complexity of them, and the need to have some standard algorithm anyway. Now, the problem with modeling languages was that you need to learn a new language, okay? And there's some overhead in translating it. So you couldn't quite make it as efficient as writing a well-tuned program to do it, okay? And if you were really an enthusiast for some programming language back then, maybe you didn't want to use another language, but there are many advantages that this makes essentially faster cycles, more reliable modeling, more maintainable models. Okay? So this really enabled people to work with the form of the linear program that I wrote down instead of with the other one. So I think this model-based optimization was really forced, really came about because of people trying to use linear programming. And so here's an early paper. This is from 1982 that says, the aim of this system is to provide one representation of a model which is easily understood by both humans and machines. The fact that the heart of it all is the fact that solution algorithms need a data structure which is impossible to understand by humans, while at the same time, meaningful problem representations for humans are not acceptable to machines. So this was being written then. This is pretty much just what I was telling you. Okay? And this is from a paper that described another modeling system that's still much used today called GAMS. So that originated right about this time to address just this problem. And I wrote a paper about the same time that said pretty much the same thing. Okay? And this paper did not describe any implemented language, but it led us to do this ample language a few years later. So right about that time, people were thinking about doing something about this problem. And ample is what's called an algebraic modeling language. You define some data in terms of sets and parameters. You define some decision variables. And you minimize or maximize a function, and you put the constraint. So it's just like I showed you. This language does the same thing as that math that I showed you before, and has the advantages that it uses familiar forms. It's very powerful. It can describe any sort of optimization problem like this, and it's been proven in a lot of circumstances. So in experience, it's turned out that this is a useful way to write lots of problems that people want the solution to. Okay? So for that example that I showed before, we can go back and look at it. We can go back here, and that one is called Steel T. So there's my model, and you can see here's all the parameters, and if I scroll down a bit, you can see that it has an objective here, and here are the three constraints that I described, and the upper bounds on the variables are here. And so I can write that same model like that. And that's the idea, is that now that's what I give to the computer, not a computer program. And then I can go here and there's some data for a small instance. But if I want to make a much larger instance, I just give it more data. Okay? This is only for t = 4 periods. But if I want to do it for 40 periods, I can give it a much larger data set if I can just find the right data. Okay? It only has 2 products here, but it could be just as well for 10 products. And so then if I go here and I reset it, and I go back and I'll just clear this out, models, mod. And for this problem, I want a solver that's a linear programming solver. And I guess the best known linear programming solver these days is Cplex. So I can use that one, for example. And just to show you the size of it, I can do option show stats 1, solve, there. So you see, this is not a very large one. It solves right away. Okay? And then if you want to know what the solution is, okay, so the production variables are called make and display, and the sales variables are sell, and here's the inventories. So, and then that all can be exported to any other system. And so you can see that in this case, you never got near the algorithm. You didn't worry about telling the algorithm what your matrix was or anything like that. You just did it. And this is really what really drove model-based optimization, because here you're thinking entirely about the model, and you stop thinking about methods. Okay? The method is the Cplex, and every year Cplex comes out with a new version that's faster and better and more comprehensive and so forth. And you don't worry about it. So then this just shows the same thing here. The data, and I solve it, and here shows that, well, if I don't want to solve it with Cplex, there's an equally good solver these days called Gurobi, and it will solve it as well, and there are others as well. So another thing, this is sort of solver independent. You can use any of these solvers, and sometimes one is better, and sometimes another one is better. So in this case, it's so small that both of them solve very fast. So there's that's sort of the background of why model-based optimization came to exist, and why it was worth developing these modeling languages. And so part of this talk is to say, well, what is the state of things now, and where is it headed? And so I'm going to talk about several things here. One is, where is model-based versus method-based today? Okay. Does everybody do model-based optimization, or are there some areas where it's still method-based? Where is it headed? And another thing is, what has happened with these solvers? This whole approach is limited by how good the solvers are and what they can solve. And so how far have the solvers progressed in this field? And the third thing is, what developments have there been in these algebraic modeling languages? So I'll show some simpler examples, but where are they headed? And what are people doing with them? And there are some things there that actually involve programming languages and are maybe not what you would expect. So first, let me talk about model-based versus method-based. And model-based optimization is standard now for a lot of things. Okay? People take it for granted. Many application areas where people are really interested in the model, and if CPLEX can go off and solve it, or Gurobi, that's fine. They're not really interested in devising new algorithms. Okay? All kinds of users. Anybody who's taken a class in some sort of optimization sort of knows the background to use this kind of system. And other people with technical backgrounds. So maybe your background was in economics or chemical engineering or whatever, but you had to take a calculus course and you know what summations are. And it's easy to pick up this kind of idea for writing optimizations. And even people who have never seen it before, okay, find this to be a good way to get into it. You can relatively quickly try out some model and get going. You don't have to learn a lot about the mathematical and computational side of optimization. You can concentrate on the application side. Okay? And trends tend to favor this. The off-the-shelf solvers get better and better. And as they get better, there's less and less reason to be involved with the solver and more to concentrate on the model. And also the data access has gotten easier. And that's something that's really changed in the last 10 years, that there's, you hear about big data all the time. You can get detailed data from all sorts of things. And so really what you're concentrating on is what model should you use to do something with that data. And you can be sort of somewhat confident that the data values you get are meaningful, and concentrate on what to do with them. So what about method-based optimization? It hasn't entirely gone away. Okay? So for very large specialized problems that are embedded in some huge application, it may be worth doing your own method. So for example, in the United States, there's a huge package delivery company called UPS. It was originally United Parcel Service. And they have trucks that deliver some millions and millions of packages every day over the entire country, and in fact, many other countries as well. And they have a program that optimizes the exact route of every driver, and down to the point that it discourages left turn. In the United States, they drive on the right, so it discourages left turns because more accidents are made turning left against the traffic than turning right. I mean, it's just incredibly detailed. And so for something like that runs a whole huge company, it can be worth building your own method, because such great resources are devoted to it, and that you can afford to hire 100 programmers to maintain the code. Okay? And so that's one thing. Another one is like Google Maps. If you've seen that, I mean, what does Google Maps do? It solves shortest path problems over and over again with many constraints. Right? You can't go down one-way roads, and you have to go, there are certain things you can do at an intersection and certain things you can't. You can't turn left here and so forth. And so that, again, I don't think that Google is using an off-the-shelf shortest path method. They have written all sorts of complicated things there. But they're solving, millions of these problems. So that's one place where you still see it. Another is in what are called meta-heuristic frameworks. You may have heard of like simulated annealing or evolutionary methods, also called genetic algorithms. And these are for problems, optimization problems where you just can't get it into a algebraic form. There's something really complicated about the constraints. It's very difficult, and so what you try to do is give up on finding a provably optimal solution, and instead just use a heuristic that finds better and better solutions until eventually you stop it and take the solution that it's found. And people who work on these things don't really have, the trouble is that you have to sort of devise an approach within this framework for every different problem. So an evolutionary method is not really one algorithm, it's an approach to solving problems, and you have to actually look at your problem and say what the solutions are and which solutions are neighbors to other solutions, and submit a certain amount of information there. And so when people work within these frameworks, they tend to focus somewhat on the method that they're going to use, okay? And also in computer science, well, in computer science, you know, that's the one field where everybody likes to program. And so the idea of writing a program to do something doesn't seem as bad to them, okay? In fact, it appeals to them. And so there are various areas in computer science where sort of method-based approaches are still pursued. One of them is this area of programming in constraints, which is really just a different approach to handling some really difficult combinatorial problems. Another one is, you know, all this learning, what's called deep learning, which is really a new version of neural networks, and really training your neural network to recognize whatever it is you want to see, recognize faces or moves in some game is really an optimization problem. You have many parameters in that neural network, and you have to choose the parameters appropriately to sort of minimize the error. And so they've done many, like they write their own programs to do this sort of thing. Okay? Even so, I would say that the trend is more toward a model-based framework. And partly it's because the solvers get better and better, the general solvers get better and better. And it becomes easier and easier to use these models within applications. And also, I think it's that it's rubbing off on these people somewhat. So that even people who do these meta-heuristic frameworks or these kinds of things have begun to think in terms of systems that are more model-based, that let the user focus more on the model and less on the programming. So I think even then it's moving in this direction, but you should expect if you talk to someone in computer science, they may not like this idea of modeling languages because it gets in the way of this great program that they're writing. Okay? And so that's what I want to say about, you know, one versus the other. Then as for solvers, the really big solver class is what's called mixed integer linear, which is linear with integer variables. And it was the advent of solvers that were able to do this effectively that really made this modeling take off, because this greatly increases what you can do. This is the most popular large-scale model type. It lets you model not only quantities that take integer values, but it lets you model logic by having what are called 0-1 variables that can only take 0 or 1. And once you can model logic, you can do much more to model complex situations than if you only have continuous variables. There are some extensions to quadratic that I won't spend any time on, but it's also the most successful solver category in terms of solvers sold. There's a very complicated approach that they take to solving these. So a huge amount of effort's gone into producing general purpose solvers that can handle integer variables in a wide variety of circumstances. And they have all sorts of routines initially just to sort of pound the problem down and make it easier and easier. And then they do this sort of branching search where they use all the cores in your computer. And this is a whole area in itself. And as a result, solve times have reduced dramatically, and both due to better ideas and faster computers. And you'll even see people claim that, that they're a factor of like 1 billion faster than they used to be, although that's a bit exaggerated. I mean, they're basically solving a very hard problem, and all that says is that, well, the time can blow up, and now when you work really hard, it doesn't blow up so much anymore on those problems. Now there are other bigger problems that time will blow up on, but even so, it's impressive that the many orders of magnitude faster on given problems. So problems that were considered completely intractable before, now you throw them into CPLEX and it solves in 5 seconds. And the improvements have continued for a very long time. So you're getting the benefit of 25 years of study of this, okay? And this area is dominated by these 3 commercial solvers. And if you look at public benchmarks, you'll see that these are around the same efficiency and much better than anything else. So it really has benefited from a lot of money poured into that. And so here's an example, in this case, of a multi-commodity network. And I want to show that everything in blue has to do with the integer variables. There's a fixed cost for shipping, minimum total shipment size, maximum number of destinations. And there are these 0, 1 variables that are 1 if a product is shipped and 0 otherwise. So this makes it, now takes it out of the realm of pure linear programming. It's mixed integer programming. You can't, if you just solve for these, they might come out fractional, but you can't let them be fractional. And so now there's a fixed cost term here that depends on this. And in the constraints, you see that there's a constraint here. It says when Yij is 1, that fixes all these Xijps to 0. I mean, when Yij is 0, it fixes all these to 0. When it's 1, it just goes away and it becomes an upper bound constraint. And there are a couple more constraints like that that involve the X's and the Y's that say that, and if you analyze these, which I don't have time to do right now, they say things like there's a minimum amount you have to ship if you ship anything, or the number of destinations served by an origin must be at most a certain amount. And so this really broadened the scope of optimization. And I can show you here that again, there's an ample formulation. I take a constraint, objective like this, and I write it in this form. You can see that now here's the fixed costs. Now my variables are called trans, how much to transport, and use, which is whether I use a given link from I to j. And here are all my constraints. I take all those constraints I wrote before, and I write them down in ample. And now I put in some data. Here I've got only 3 origins and 7 destinations and 3 products, whole lot of costs. And I send that to a solver like Garobi, and it spits out an answer. And now you can see that in addition to using the simplex method, it does a certain number of branch and what are called branch and cut nodes. So it actually has a tree of nodes of solutions that it's exploring to find out, to prove that this is the best one. And then you can do the results here. And so this solver development has made a big difference to people using model-oriented optimization in all fields, because it just greatly expanded the power of the models that they could write. You see all these things like fixed costs and minimum shipments and limits on amount, on service and so forth, are all sort of logic constraints. And this enabled them to handle that logic. Okay? And now here's a completely different example that's been proposed recently, which is to take a model-based approach to linear regression, which is something you learn in statistics. You're given an observed vector and a bunch of regressors, which are different data series. And you want to choose some multipliers for these data series such that the vector of observations you're trying to predict is approximated by the sum of some combination of these, okay? Some linear combination, okay? And you want to do this in a way that explains the y convincingly. So you don't want to actually use all these p regressors. You want to find a way to throw most of them out and get a small number of them where your model here, where your betas are a good explanation. Okay? And so a method-based approach to linear regression, which is the traditional one, is you solve some problem that minimizes the amount of error, And then you look at the regressors and their coefficients, all the betas, and you throw some of them out. You say, well, this beta is so small, it's not statistically significant, so I'll throw that one out. And you throw some out and you try again, and then you reevaluate. And maybe you throw some more out and you bring a few more in, and you keep going until these are judge satisfactory. And you'll see people will write that, well, there are various ways to do this, but really it's more of an art than a science to figure out which regressors you should keep. And different people faced with the same data will come up with different solutions. Okay? And the model-based approach is to build a mixed integer optimization model of the best choice of regressors, and then send the model and data to Cplex or Gurobi or Express. This is what's been proposed now. And the integer variables are, I'll show you here in a moment. Oh, this is, by the way, based on some recent paper where this was described in detail. Here are the observations, here are the regressor values, okay, for M observations and N regressors. And the variables are the betas, but there's also a variable Zj, which is 1 if beta is not 0, and 0 if it is, okay? And so Zj is a 0, 1 variable that tells you whether a regressor is used, okay? And so we actually include that in the optimization. Instead of putting that outside and keep trying different things to decide which ones to use, we just let the model decide it by picking these 0, 1 variables. And the objective is, this is just the sum of squares that's used in optimization normally. And I mentioned earlier that these solvers have been extended to convex quadratic problems. And this is an extra term here which improves the robustness. It essentially says that we'll add a term which sums the absolute values of the betas. Tends to give better results. It's called a lasso term. And then there are all sorts of constraints you can put in here. The first constraint here just says that if Zj is 0, then beta j is 0. So it says if you set this to 0, then you don't use it. Okay? And then all these other ones say things like, at most k regressors may be used. Well, that's just this linear constraint. Okay? And then for every pair of highly collinear regressors, only one may be used. Well, that just says that their corresponding z's can't both be 1. Okay? So you can throw that out. Or, and then there are some regressors that are just transformations, square roots and squares of other regressors. So that says if you have a combination of all those different functions, you can only use one of those. You don't want to have both a regressor and its log in the solution. You can specify that some must be in by setting their z's to 1. And if you had a previous solution and you want to generate a different one to get a variety of solutions to look at, there's a way of saying that, well, not all of the ZJs that were 1 in the previous solution can be 1 in the current solution. Okay, this says that if I sum them all up, their total has to be less than the total number of them minus 1. Okay, so this is using 0, 1 variables to specify all these requirements in the optimization problem. Okay, and then you can go off and solve this problem. Okay, and so here's a quite different example of where model-based optimization can change the way people think of doing things. Okay, and since I'm almost out of time, I won't say much about this here, except that there are many situations where you have constrained nonlinear problems as well. So another big thing is, I only showed you unconstrained nonlinear problems, but there are now very powerful solvers that will handle all sorts of constraints in nonlinear problems, and will solve in all sorts of ways, as you can see here. Okay, and there are all sorts of algorithmic approaches as well. So there's this whole rich field of nonlinear optimization, and there are all sorts of solvers available, and some of them are commercial, and some of them are academic, and some of them are free. So there's much going on there. And an example of this is optimal power flow, which is given a network, find minimize the total amount of power generation needed. And the problem there is that the power generation obeys something which I am told is called Kirchhoff's law, which is nonlinear. So you just can't write a linear model for power generation because electricity just does not behave in a linear way when you ship it over power lines. And so here's just one test case. I have this model here. Just briefly, I can show you, it's this OPF. So this is just a model, okay? Whoops, that's not it. I want oh, I know what it is. No, I want OPF.mod. There we go. So there it is. This is the whole model. Of course, the first page is just test, but lots of parameters, and then various kinds of constraints and complicated sets, and very complicated definitions of variables in terms of other variables, and here's the objective. This is the power. You see that's not very simple either, and these are all the constraints. And you can see in here that there are some sines and cosines, for example, so that this is definitely not linear at all. Okay, and so this very complex model gets set up, and this just shows what happens when I try to solve it. And you see that a lot of variables are eliminated and substituted out, okay, because they're trivial in some sense, and I end up with 1,400 variables and 1,300 constraints, okay, and but it's actually solved quite quickly, and in 20 iterations. I mean, this is not actually big. People solve much bigger ones as well, but well, I just wanted to show that nonlinear optimization is not limited to the simple examples that I used at the introduction here, okay? And then I'll finish up by saying a few words about where algebraic modeling languages are going. And there are actually two design approaches to them now. One is what I'll call declarative, which are these specialized languages like GAMS and AMPL. And the other are executable, which are libraries for programming languages that allow you to do something like a modeling language inside the programming language. Okay? And there are also two different approaches, or several different, for marketing. One is some of these are solver independent, like the AMPL I showed you, but other ones are built by the developers of a particular solver to serve their solver only. And then some of them are commercial and some are open source as well. So the declarative ones that are solver independent are various commercial systems that have been around for a long time. And there are some open source systems as well. And these have been enhanced in many ways, okay? Better development environments and tools for deployment, various programming features to write little scripts to do things, various data sources that they can do, more general constraints. Okay? So these have been developed more and more over the years. Okay? Now, solver-specific ones, the developers of these solvers have their own and analytics platforms and so forth. Some of them have their own languages. Like if you know the SAS language, which was originally statistics, but is now they call themselves an analytics platform. They have something called OpModel. And if you looked at a page of OpModel really quickly, you would think it was AMPL. It was actually quite similar to it. And they found it necessary to have that in their system in order that people could generate these problems because they wrote their own solvers. Okay? So then there are these executable modeling languages. And the idea is inside a programming language, you create something that looks like a modeling language. And you do this by allowing operators like plus and equals, but redefining what they mean. So when they're used, you have certain objects that are like variable objects and parameter objects and expression objects. And when you combine them with these symbols, instead of just adding or comparing, they actually generate new objects like constraint objects and objective objects. And so you can have a programming language that looks where it looks like you're writing a model algebraically, sort of, okay? Even though you're working within the language. And the advantage is that then you can do your modeling and your application development all in one language. So if you want to do it all, and I'll show you there are quite a few languages you can use, and it gives you better access to some advanced solver features. So if you find that your problem is so difficult that you want to go in and actually do some things in the middle of the solver run, Well, it's easier to do it with this approach because it's in some sense lower level, closer to the solver. Okay? The disadvantages are that it's still harder than I think than a specific modeling language. Okay? If you put a modeling language inside Python, it still looks like Python, and you better know some Python to use it. It's still a little bit harder to find the bugs, and you have to worry more about efficiency. Here's an example. Gurobi has its own Python modeling language. So you can write something like this, model.add constraints, and that looks like pretty much like a constraint for I and for j. Or here's another one for I, j, and arcs. Add the sum of flows for h and commodities, less than or equal to the capacity. This is just an expression for the name of the constraint. You might wonder, why do they have, what's this quick sum thing here? They have an explanation of that. And well, it's much more efficient for building things. But it's not the fastest approach, and they have all these here. And I think this, this is where you run into efficiency problems. That because you're implementing it inside the programming language, okay, there's a certain amount of overhead and things that you don't have the flexibility of in a special purpose modeling language that you would have to just implement it yourself and make everything more efficient. So Cplex has a C++ interface like that. Gurobi has a Python one. MATLAB has one for their optimization toolbox. And then there are many open source solver independent ones. In fact, there's one for the R language too now. And so this is, again, what you might. There's quite a selection of these. And so if you want to take a model-based approach, there are quite a few ways to do it, let's say. So that brings me to the end of my presentation. I hope you found something of use, and I'm open to questions.
Yes. In terms of model versus method,
yes.
two differences that you mentioned. It appears to me that for a company, a small company that's getting into OR applications,
yes,
is likely to benefit from a model-based approach.
yes.
But still, in order to get that model up and running, you sort of need either a sort of a consultant who's an expert in method-based techniques, or an internal person who's dedicated, who's still an expert in the methods space.
Yeah. It depends what you end up generating. So I've seen examples of companies where somebody just built the model and they sent it to Cplex and it solved it. And they never did learn anything about the methods. And so what you describe only happens if you decide to implement a very complex routing, say, model. And routing is known to be particularly difficult for mixed integer programming. And chances are that you can't just build a whole model and it's going to route all your vehicles magically. You're going to have to use some tricks and stuff. And that's where you need to hire somebody or get a consultant to think in a more method-based way, I would say. But I think that the trend over the years has been that the number of things you can solve by just writing the model and leaving it to the solver has increased. And that's been responsible for a lot of greater use of optimization. Now, you're right, you could go from one to the other. So you could start with a small model that works fine, and at some point you get stuck, and you go get somebody. Okay? But, yes?
For many companies in developing countries like India, some of these commercial solvers, I think, are still very costly. And recently, I did something for a company where they used this optimization on cloud from IBM.
Yes.
And that seems to be very cost effective as well. So is that the trend as well?
Yes, people have asked us about that. It doesn't, so I think that IBM's optimization on the cloud currently doesn't interface to modeling languages very well. You sort of send it a file and it generates a solution and it says, okay, here's the solution. Now you have to do something with it. And so So I don't know, we were just talking to a customer actually who was trying to figure out whether they needed to use that or whether it'd be more cost effective to buy one time a solver and put it on a local machine, or maybe buy one time a solver and then get a cloud machine and put it on there. And I see a lot more activity in trying to use cloud solutions and services and that kind of thing, rather than buying up front the software and running it locally. Yes.
So I have a more for technical question.
Yeah.
So one is that in economics, we most of the time have problems where objective functions are non-linear, mostly concave.
Yes.
And you have this discrete time. So infinite horizon problem, at every point of time you have linear constants.
Yes.
Connecting this period to next period.
Right.
The state variables are equal,
Right.
and then the objective functions are concave at every point of time.
Right.
So one of the biggest problems that we find in that kind of things is this curse of dimensionality, right? The number of state variables going beyond 5 or 6 makes it very difficult to solve. That is what I mean, kind of puts a very large constraint on what people can do. So with this kind of solvers, do you think it would be a little easier to deal with? We mostly use MATLAB.
Yeah. So there are a few solvers that handle nonlinear objectives and discrete variables. One is Nitro, which finds local solutions. If you want global solutions, the most popular one is called Baron, and there's also an open source one called Quen. And with them, it's possible to send these models. I mean, they're connected to the modeling languages, so it's possible to send the models and see how they do. And and they may be better than what is available within MATLAB to solve those problems. So the developers of MATLAB have recently put a lot of resources into increasing their optimization activities to the point that they implemented a modeling language in MATLAB inside it to drive their optimization toolbox. But it's still true that there are problems for which you need to go outside of MATLAB and consider one of these other solvers for really difficult problems. At least with what they have today.
So is there a solver that can deal with nonlinear problems and logical constant thinking?
Yes. So if you're willing to use 0-1 variables to implement the logical constraints, then there are a few that will take that. So like those ones I mentioned, Nitro is the main commercial one that can do that. And Barrett. Yeah, well, if you change the logical constraints into algebraic constraints using 0-1 variables, then they can handle it. Yes. So they don't know enough that you just say either this or that, and they don't know what to do. But if you define a 0-1 variable and program that into an algebraic constraint, then they can handle it. And so there are several. Now those are hard problems. So the linear mixed integer problems, solvers handle today routinely ones with millions of variables. But if you have nonlinearities, I think that you shouldn't expect to handle such big problems.
That's a problem. I know there is a problem. This is really giving us a problem in terms of solving. Non-linear as well as your if-then else type or logical constraints.
Right.
The price is greater than this, then this is do this, and if price is greater than this, then do this and other. So that is not quite well happening in AMA complex.
Yeah, so you need to, I mean, then you have some formulation challenges.
So then can we deal with heuristic problems in AMPL? I mean, a heuristic formulation of a problem, MetaHeuristics or...
No, so it's not connected to any MetaHeuristics.
But see, in simplex there is an option, right, for a heuristic method of...
So all of the mixed integer solvers have heuristics in them, which they use to find good feasible solutions. And for other purposes, but they have really good heuristic feasibility, which which is sort of what you think about as being the typical optimization heuristic, right? It's trying to heuristically find a good solution. And so that's built into all of them. But those aren't necessarily the meta-heuristics that people implement independently. So, I mean, those are heuristics specifically designed for mixed integer programs. So. Thanks in terms of that.
Okay, on behalf of the institute, I'd like to thank Mo for coming here. I think spending 4 days here and giving an interesting talk. It looks me that I'm attending my large-scale optimization class in Northwestern Rukmi. So thank you very much for coming here and on behalf of the institute.